Imagine you're a student and you have to take a number of courses to graduate, but some of these courses have prerequisites, which means you cannot take a course without actually taking its prerequisite courses. For example, you cannot take advanced engineering math before taking engineering math. Suppose you have 5 courses. We'll name them characters from the English alphabet for now. Now let's try to draw connections between these courses. A directed line from one course, course A, to another course, course B, means that you need to finish course A before you can take course B. Let's say the connections look something like this. Now here's the actual question. How can you determine the order in which you can take courses such that you can take all the courses? Let's try to order like this. This doesn't work because in order to take A, you need to finish B. Can we do it like this? No, because you need to finish D before C. But if you order it like this, we'll be able to take all the courses. This kind of ordering is called topological ordering of a graph, and the algorithm for finding this is called the topological sorting. In this video, we're going to look at LeetCode problem number 210, course schedule. In this problem, you'll be given two things, an integer n and a two-dimensional array prerequisite. First, let's talk about n. N is the number of courses you have to take. It's also the indication of the labels we're going to use for each of the courses. If n is 5, courses are labeled 0, 1, 2, 3, 4. Now, we also have a two-dimensional array prerequisite as input. This particular 2D array only has 2 columns and many rows. A single row will have 2 values, both values indicating different course labels. If we call them AI and BI, it means you must take BI before you can take AI. We can use this information to draw connections like we did before. And the problem expects you to return the topological ordering of the courses. For understanding how to solve this problem, you'll need to learn 3 things. 1. Graphs. We know the input looks like this, but we need to convert it into something like this. This right here is something that we call graph. A graph data structure has several vertices or nodes. In this case, a course is a node, and we have edges. In this case, we have directed edges to represent the direction of dependency from one course to another. We need to represent child courses. We do that with a list of courses within each course. So that's how you represent a graph. To be able to apply topological sorting, we need a directed acyclic graph. So what is a directed acyclic graph? We already know what a graph means, and we know that we have directed edges in our graph, so that makes it a directed graph. Acyclic just means that there are no directed cycles, like in this one. If we have a cycle in our course scheduling problem, it just means we'll never be able to complete the courses. Because one course depends on another course that depends on the first course, that just doesn't work. So our course scheduling problem deals with a directed acyclic graph. 2 is depth first search. If we have to determine an ordering from this graph, we need to be visiting each of the courses. So we need to be using some sort of graph traversal algorithm. For this, we'll use depth first search. Depth first search means you start at any node and explore as far as possible along a single branch. Once we reach a node having no further child nodes to explore, we drag back to the previous node and explore the unexplored branches of that node. If we keep doing this, we'll end up visiting every node in the graph. Of course, this means that we need to keep track of the nodes that have already been visited. If we don't, we'll never finish exploring the graph. For this reason, we'll keep a state variable within a node and mark it as blank initially. Once we're in the visiting path, we'll set it to visiting. Once we have completed visiting this node, we'll set the value to complete. For implementing DFS, we use a recursive function. This will return either true or false. If it returns false, it means there is a cycle. This will take in a single node. First, we'll check if the state of the node is visiting. If it is visiting, then we have found a cycle and we need to return false. The state is blank. We need to iterate over the node's children and call DFS on each of the child nodes recursively. 3 is topological sorting. We need to slightly modify the DFS to find out the topological ordering of the graph. First, we'll iterate over each of the nodes in the graph. If the state of the node is blank, we'll try to call DFS on that node. If it returns false, this function will return null. We'll create a stack data structure and pass it along the DFS call. A stack data structure means you can add something into it one at a time by using something called push operation, and you can take something out of it one at a time using pop operation. The only thing you need to understand is that the last thing going into the stack will be the first thing coming out of it. Just like if we keep a stack of plates, the last plate that goes into the top is the first thing you can take from the stack. In the DFS, once we have completed searching through all the child nodes, we can add the nodes label into our stack. Why? If we were able to run DFS on each of the child nodes, it means that those child nodes were already added to our stack. We know that the current node should be coming out of the stack before its child nodes. Ultimately, if we keep popping from the stack and adding to some list, the list will give us the topological ordering. If you enjoyed this video, please consider subscribing and make sure to leave a comment as well. See you soon.